Today we'll be covering the solutions of the first intern mock test. Here's the first question. You are required to convert a given integer n into an arbitrary base b. Let's first understand what a base is. A base 10 numeric system uses 10 total digits to represent all the numbers. A base 8 numeric system will use only 8 digits. Because we only have 8 digits, after we go from 0, 1, 2 all the way up to 7, in order to move to the next place, we will introduce one more digit on the left side. So when you read 1, 3 in a base 8 system, we can understand this as 8 times 1 plus 3. Similarly, when you read 1, 3 in a base 10 system, that's 10 times 1 plus 3. In a base 12 system, for example, we will have a total of 12 digits. So here, because we only have 10 normal numbers, I'm introducing a and b as new digits. Therefore, if we are given the representation of a number in any base, all we need to do is multiply 1 with the rightmost digit you saw, plus b times the second rightmost digit, and so on. This will give you the value of x. In our question, we are given the LHS x, and we are required to find the following decomposition. Now, it's quite evident that here the first digit or the rightmost digit is simply nothing but the remainder of x with respect to b. But how do we find the remaining digits? We will observe that if we just divide x with respect to b, that is, we find the integer division, we will get the following decomposition. Now, the second rightmost digit has become the remainder again. Now, if you simply repeat this process over and over, you will get every single digit of x. So if I were to divide x with respect to b square now, we will now get the third digit on finding the remainder. Here's the code that accomplishes what we described. So first we take our inputs. We will clear the base case where n equals 0, because this is the only case where we want to begin our answer with a 0. Then we'll create a stack and we'll simply push in the remainders one by one and incrementally change our n so that we divide by b. Finally, the question requires us to clear out the leading zeros. So we will clear out any leading zeros and we'll print out our answer. Note that I'm using a stack here because we calculated the values from the rightmost digit to the leftmost digit, but obviously we have to print them out from the leftmost to the rightmost. You could do this by reverse iterating through a vector as well. Now let's discuss the time complexity of our solution. Note that at each iteration of our loop, we had taken the value of n and divided it by b. Thus, we will have a total of log b n total iterations. This gives us a time complexity of O of log n.
Today we will solve problem B, Varun's cooking quest. The problem summary is, Varun wants to learn as many cooking techniques as possible before a culinary contest. Each technique takes a certain number of days to master, and Varun has a limited number of days before the contest. You are given n, the number of techniques available, d, the number of days left, a list of n integers where each integer represents the number of days required to learn a particular technique. Your task is to determine the maximum number of techniques Varun can master completely within the given d days. So our intuition to solve this question would be a greedy approach. Why would greedy work here? Firstly, so to maximize the number of techniques Varun can learn, he should prioritize doing techniques that take less time, because learning smaller ones first allows him to accumulate as many techniques as possible within the given constraint of time limit, and so he can maximize the number of techniques he has learned in the same time. Let's consider this example of 4 numbers and let the maximum number of days Varun can do the learning for be 10. The given number of days required are 3, 6, 5, and 1. Now, if Varun solves each technique one by one, then in that case, he'll only be able to do two techniques, as 3 plus 6 will be 9, and 9 plus 5 will give 14, which exceeds 10. And therefore, he'll only be able to do 2 such techniques. However, if Varun solves it greedily, that is, he does the technique that takes the least amount of time first, that is 1, and then he takes the second technique 3, and then 5. In that case, he'll be able to do 3 techniques instead of the previous 2 techniques, which is much better approach. Now, so how will we solve the question? Firstly, we'll sort the list of required days in ascending order. This ensures that we'll try to learn the shortest techniques first. Second, greedy selection. We will initialize a counter IDX and a variable days with value 0. We will traverse this sorted list and accumulate the time for each technique until the number of days required exceeds D. Finally, we'll print IDX, which is the number of techniques that Varun can learn completely within within the specified D amount of days. Now, this is the code implementation for the question. We have a vector which t, which is taking in the number of days required for each technique. We then sort t. After that, we initialize the variable days to 0 and a counter idx. While the number of days is less than d, the value of idx is less than n, since the number of techniques that he can learn cannot exceed n. And the day and the number and the value of days plus the number of days required to learn this particular technique is less than d, less than equal to d. We will increase the number of days required by this technique to days variable, and we'll increment the idx counter variable. Finally, we will print the idx variable, which is the number of techniques that he can learn. The time complexity for this solution will be n log n, since sorting will take the maximum amount of time, that is n log n.
Okay, now let's solve problem C, power positions. So in the question it says that Pava has a array consisting of positive integers, and then he experiments using the array. In the experiment, at each step he chooses two elements of the array I and j, such that ai and aj are positive. Alright, and now if ai is greater than aj, he replaces ai by ai plus aj and changes aj to 0, and if aj is greater, he replaces that by ai plus aj and replaces ai to 0, and if they are equal, he can replace any one of them with ai plus aj and the other with 0, right? And now he does this multiple times, and each time he notices that one of the elements will become non-zero and the rest all elements will become 0. So he needs to find uh, such elements which can become non-zero given a optimal set of operations which he performs, right? So now let's take an example to solve this problem. Okay, now one of the given examples is 198, right? Now if he wants this element to be non-zero, what he can do is take all the elements smaller than it and add to itself, right? So now he will choose 8, the next biggest element, add to it 17, 0, 1, and now when you compare these two, this will become 18 and these two will become 0. So 9 is a possible candidate, the second element is a possible candidate. Now what about we try to make this 0 non-zero? That is, what we can do is we have 198. If we choose these two, obviously this is the element that will get changed and not this element. So what we have to do is we'll choose the smaller element, which is 1, and try to add it to 8, 099. Now these two become equal, and now when we try to change this, what happens is this can become 0 and we can make this 18. So in this case 8 can also be made non-zero, but we cannot make one non-zero because whatever of the other two elements we choose, one is going to get annulled, so we cannot make one non-zero. So this question can be solved using a greedy approach, as we can see from here. We can see that for each element we try to add up the element smaller to it with this element and check with the current element and check if the element before that, that is the element greater to it, can be can we make the current element equal to, at least equal to that element by making the adding these elements, right? I will show you another example. Okay, so let us take an example like 1 2 3 4 5, right? Now can we make 5 non-zero? Yes, we can. If we add all these elements to 5 one by one, it will be obviously greater than 1. And then can we make 4 non-zero? If we add all these elements together, it will be obviously greater than 5. Therefore, we can make 4 non-zero as well. Can we make 3 non-zero? Yes, we can make 3 non-zero, because if we add these 3 elements, it becomes 6, which is greater than 4, and therefore this element, the third element, can be replaced with 10, which will become greater than 5, right? So in this way, all we need to check is um, arrange the sort the given array in descending order and check for a current element, say this element I. If the suffix sum after suffix sum till the elements which occur after it is greater than equal to the element before it. That's all we need to check to solve this question. Like, yeah, let me explain you with a sample code. Yeah, so now we are taking the input, and then we are sorting them in reverse order. um Initially we are storing the answer to be the first element, the greatest element, which can always be made non-zero by just adding it with all the other elements, which is obviously possible. And we maintain a suffix sum array, because to be done in linear time complexity, this is to be maintained, because for every element we just need to check if the suffix sum till that point is greater than equal to the element before it, that is the element greater than and before it, right? So after we sort, to make sure that if a current element is equal to a previous element, it just adds up to the answer, right? Because if we two elements are equal and one can be made non-zero, the other can be made non-zero, the order doesn't matter. So if current element is equal to the element before it, answer is added. Otherwise, what we do is we take the suffix sum and check if it's greater than the previous greater element, and if it's greater, we add it to the answer, and we update the previous element. And also, if this is not possible, we break the array, because once it becomes not possible uh, for any other element after it, say if it becomes not possible at first index k, and then say for any other index k plus I, it will be not possible, because yeah, if it at this point we'll get stuck while adding the suffixes, so it won't be possible. uh, Let me give you an example for this as well. Say we take 100, 4 3 2 1. For 100 we can make it non-zero, and now for 4, while we add these 4 elements, it becomes 10, and this is not greater than 100, so this cannot be made non-zero. 4 cannot be made non-zero. But so there's no use considering the elements after that, because even if these can be made greater than 4, that is, if even if this can be made greater than 4, that is, we get 6 here, which is greater than 4, so the third element can be made 10, but it's of no use because it cannot be made greater than equal to 100. So we need not check further after sorting in descending order, right? Now, so we just break when we find an element which cannot be made greater, and then we just output the answer. For the time complexity of the solution, it's order of n log n. This is because the sorting step takes the time complexity of the sorting step is n log n, and after that suffix array can be created in linear time, and the processing also can be done in linear time, but so the sorting is what dominates here, and therefore the time complexity is n log n. Thank you. Okay, now let's solve problem D, rainfall strategy. Tushar owns a long narrow farm divided into a sequence of land plots. The weather spirits offer to send rain clouds to his water-rich fields, but there's a catch. If any plot receives rain from more than 2 clouds, it will overflow and damage the crop. They provide Tushar with a list of clouds he can summon, where each cloud waters all plots between two given endpoints. Tushar wants to choose as many of these clouds as possible without causing any plot to be rained on 3 or more times. Okay. So he asks our help to find the maximum number of clouds. Alright. Let's take an example to check how the thing works. Now, one of the given sample examples is the endpoints are 1, 2, 2, 3, and 2, 4, 8. So, if these two in here, if these two clouds are made to rain, so the area covered will be 1, 2, 3, 4, and this will be covered twice, right? Because 2 is overlapping. So, this cannot be made to rain if these two are made to rain. And similar is the case if these two are made to rain, this cannot be made, 2, 4 cannot be made to rain, and so on. So we can see that we need to essentially divide the clouds into two groups such that within each group no clouds overlap with each other, right? So that's how we are going to solve this question. The approach is like this. We consider two groups, each to be categorized by the last endpoint which we have covered till now, right? Say let them be last one and last two. In this way, we can add a cloud to a group if its starting point, say S, is greater than the ending point of the previous cloud in the either of these groups, right? So our greedy strategy to solve this question would be to sort the clouds in ascending order of their endpoints, and then process them one by one. Check if a given cloud, the current cloud which we are in, its starting point is greater than the ending point of either of these, so that the clouds don't overlap within each group, right? Also, whenever a starting point is greater than both of these, we will add it to a group which has the the higher endpoint. Say last one's endpoint is currently at 5 and last two is at 7 and starting is at 8. We will add this cloud to 7, the second group, because then we can ensure some more um, space for a cloud to be added within, like, say 6 or 7. So to ensure that we add it in the the second group. Now let's see a sample code and I'll explain that as well. Yeah. So we are creating a cloud or a vector of pairs, vector of pair of integers. Yeah. So we create a vector of pair of integers and then take the clouds as input, and then we sort them according to their endpoints, right? Ascending order of their endpoints. And if their endpoints are same, it shouldn't matter which comes lower. And now we initiate last one and last two as discussed in the strategy, to values which are lesser than 0, so that this is the minimum initiation which we can do. And then the count of the clouds, we are maintaining a variable for that as well. And now we iterate over the clouds after sorting them and check them check whether the starting point of a current cloud is greater than if it's greater than both of the ending points, we can add them to either group. And if last one, the first group cloud ends at a higher point, then we add the cloud to that group by this line, and then otherwise we add it to the second group. Now what we do if a cloud is greater than only one endpoint? Then we like the obvious way is to add it to that group where there is overlap, which is basically the point of this greedy algorithm which we are executing to find the count. Yeah, so um, we add it to, if the starting point of the current cloud is greater than the endpoint of the first group, we add the cloud to that group. Otherwise, if it is only greater than the second cloud's endpoint, we add it to that group. And finally we get the number of clouds which can be safely trained down. This is the strategy to solve this question. Why does this work? This is because at each point we are ensuring that no three clouds are in the same region, because within each group there's no overlap and there are two groups, so the maximum overlap between clouds can be two. And by sorting them in increasing order of endpoints, we are ensuring this overlap doesn't happen, and we can add as max of clouds as possible to our answer. Now for the time complexity of this solution, it's a sorting point which again dominates with complexity of order of n log n, and we can iterate over the clouds in linear time, so this is just order of n. Therefore this dominates, and the complexity, overall time complexity of the solution is order of n log n. Thank you.
This is problem 5 of the first intern mock test. To summarize this problem, we are given an array in which we need to check if there exists an increasing subsequence such that the product of all its elements is divisible by a number k. This problem is similar to the longest increasing subsequence problem, which is solved using dynamic programming. To solve this problem, we can add one more dimension to the DP array used in the LIS problem to store the remainders at every step. We define the state as dp of I r, which is the minimum last element of the increasing subsequence formed using the first I elements of the array, and which leaves a remainder of r when divided by k. Also, all the elements are initially set to infinity. So now the transition step. Let's define R1 is equal to R times AI mod K. Our transition step is dp of I R1 is equal to minimum of dp I R1 and A of I. We perform this transition for all r ranging from 0 to k minus 1. To understand the time complexity of the algorithm, let's take a look at the loops we need. First, for I goes from 1 to n, then for j goes from 1 to I, which is the first I elements of the array, we perform the transition step for r goes from 0 to k minus 1, and then we do the transition. So this is O of n square k. Now going back to the constraints, here n square k is equal to 2.5 into 10 power 7, which is less than 10 power 8. So this will pass the test cases. But here it's 1.25 into 10 power 11, which is much larger than 10 power 8. So it won't pass these test cases. So we need to find a way to compress the 2D DP array into a 1D DP array. We can define a new state as dp of r, the minimum last element of an increasing subsequence, which leaves a remainder of r when divided by k. The transition step is pretty much the same, except that instead of using a new array every time, we just update the array used for the last element. So again, r1 is equal to r times ai mod k, and dp of r1 is equal to minimum of dp of r1 and ai. To find the time complexity, let's look at the loops once again. First, we have a for I goes from 1 to n, and then for r goes from 0 to k minus 1, and the transition step. So this algorithm is O big O of n times k, and it passes all the test cases. Finally, we just have to check if dp of 0 is equal to infinity. If it is, that means no minimum element exists such that the remainder is 0. So we can output no. And if dp of 0 is not equal to infinity, that means a minimum last element of a subsequence exists such that the remainder of the subsequence is 0. And that means the subsequence does exist. So our output will be yes. Here is the solution code for reference.